We're going to look at steps of a hypothesis test and confidence interval and do 2 AP free response released questions at the end. So just a quick review of the steps of a confidence interval or hypothesis test. Now the main difference is you don't need to write hypothesis if you're just doing a confidence interval. So the first step is to write your null and alternative hypothesis. It's usually, your null is always that it's, I got a pen. So your null is that P is equal to 0.2 or whatever the value it's mentioning, or mu is equal to 5 ounces. The difference is usually P hat 1 minus P hat 2 equals 0. Mu 1 minus mu 2 equals 0. Your nulls are always equal to what the problem is asking about, and you have to prove otherwise. So our alternatives are greater than, less than, or not equal to. With the difference in means and proportions, you have to pay attention to which way you're subtracting and making sure your sign is correct. So step 2 is checking your conditions. For the z-tests, for all of them actually, you're checking randomness or representative or a randomized experiment. Z-tests and t-tests have the n minus or n less than 10% of the population in common, and then the main difference here is your z-test has the np greater than 10, nq greater than 10, and your t-test has the nearly normal, where you check the histogram or a normal probability plot for straight enough. Your chi-square test, the data needs to be in counts. You can't use percentages in a chi-square test. You need to convert it to counts. If you're given percentages, again, it has to be random, representative, and your expected counts have to be greater than 5. You find those in the calculator. You find this by multiplying the percentages by the total for a goodness of fit test. This Lin-Reg t-test has the scatter plot needs to be straight enough. That's a linearity assumption. The residual plot needs to be randomly scattered. That's independence, and consistent spread, equal variance is your assumption. And your normal probability plot of the residuals has to be straight, or your histogram of the residuals needs to be nearly normal. So those are our conditions. The next thing we do is make sure we state that the conditions are met and name the test. That's always one of the things in the scoring guide, is that the test is identified by name or formula. Then your calculations. Now, if you're doing a confidence interval, then this is where you're going to calculate your confidence interval. So your calculations, either a z-score if it's a 1-prop z-test or a 2-prop z-test, your t-score if it's a 1-sample t-test or a 2-sample t-test or a matched pairs t-test, your chi-squared statistic if it's a chi-squared, your t, again, if it's a Lin-Reg t-test, and then you calculate your p-value. Now remember that your test statistic, whether it's z or t, is the sample value minus the hypothesis divided by the standard deviation or the standard error. Sometimes we use the z-score to calculate probabilities, and in that case it's standard deviation, but normally with the hypothesis test it's a standard error. And we have a few formulas for that. Our standard error of p hat is the square root of p hat q hat over n. Standard error of x bar, the mean, is s over square root of n. And then we have the proportions, or adding or subtracting. Remember that when we're doing the 2-proportion z-test or the 2-sample t-test, our standard deviations will always add. So that standard error p hat 1 minus p hat 2 is your square root of p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. And with that test you also have the pooled value, the pooled standard error, where you would use pooled instead of p hat 1 and p hat 2. And then the standard error for the x bar 1 minus x bar 2 is the square root of s squared over n1, s1 squared over n1 plus s2 squared over n2. Remember that variances and standard deviations, the variances always add, so we're never going to subtract in these equations. And then after you have your test statistic, you calculate your p-value using either normal CDF. If it's greater than, you're going to do your z comma 99. If it's less than, you're going to do your negative 99 comma your z-score. The same with the t-CDF. And the difference is there we have to add the degrees of freedom. Remember, our degrees of freedom is your n minus 1 for one sample, n1 plus n2 minus 2 for your 2 sample, and it's n minus 2 for your ln reg, and then your chi-squared ones determined by the cells in the matrix. So remember that chi-squared, we use the E99 because it's not always smaller than 99. And after we do our calculation, we do our conclusion. We make sure we state this in context. If our p-value is less than our alpha, we reject our null hypothesis. Remember that suitable alphas are 0.1, 0.05, and 0.01. And a lot of times it'll tell you in the problem which one to use. Our standard here is the 0.05. So when we reject, there is enough evidence to convince you that the null hypothesis is not true. This is a statement that students are still getting messed up. We're rejecting the null hypothesis because you believe that that's not true anymore. So there was the evidence. The evidence was there to say that's not true. And if you fail to reject because your p-value is greater than alpha, there's not enough evidence to convince you that the null hypothesis is not true. Remember that we never accept the null hypothesis or prove the alternative. We always have to speak in vaguer, more vague terms, because another study can come along and tell us something completely different because of sampling variation. And then the last thing is confidence intervals, the equations for confidence intervals, your sample statistics, so this would be p hat or x bar or your difference. Your critical values are your t star or your z star, and your standard error, the same formulas we did on the last slide. We have these three memorized, these three z stars. 90% was 1.645, 95% was 1.96, and 98% was 2.326. Our t star uses the tables, so you have to use your degrees of freedom for that, and the t-table that will be given to you in the exam. And then we say, I am 95% confident that the true proportion of cars speeding on the freeway is between 52 and 43%. I guess those numbers don't work out so great, but you get the idea. So we make sure you're saying this in context. This is where we add our context. This is our confidence level, right? Our confidence level, and these are our numbers, our lower number and our upper number. And then there's the other statement where what is 95% confidence mean? That's your in repeated sampling. "95% of constructed intervals contain the true proportion," let me erase that, "the true proportion or mean of whatever we're talking about," and that's your context. That is your confidence level interpretation in the unrepeated statement. Okay, so let's look at an example. So we may have done this problem already, but let's look at it. This is high cholesterol levels in people can be reduced by exercise, diet, and medication. 20 middle-aged males with cholesterol readings between 220 and 240 per deciliter of blood were randomly, there's a keyword for us, randomly selected from the population of such male patients at a large local hospital. 10 of the males were randomly assigned to Group A, advised on appropriate exercise and diet, and received the placebo. The other 10 males were assigned to Group B, received the same advice on appropriate exercise and diet, but received a drug intended to reduce cholesterol instead of a placebo. After 3 months, post-treatment cholesterol readings were taken for all 20 males compared to pre-treatment cholesterol readings. The tables below give the reduction in cholesterol level, the pre-treatment minus the post-treatment in each male. Do the data provide convincing evidence at the 0.01 level, there's the alpha level given to us, that the cholesterol drug is effective in producing a reduction in mean cholesterol level beyond that produced by diet and exercise? So our null hypothesis is going to be that mu A minus mu B is equal to 0. Our null is always that there is no difference. And then our alternative hypothesis is that mu A minus mu B, and we're going to have less than 0 because if there's a better reduction in B, that means when I subtract those two means, I'm going to get a negative value. And I'm okay by if I switch it, I can write mu B minus mu A is greater than 0 as well. That's another possible hypothesis if you want to keep it positive. So we know my alpha, 0.01, not necessary to write it usually when it's given like that. We're going to check our conditions. So with the random assignment, so that's one condition that works. 10 is less than 10% of men with high cholesterol for both groups. So 10 or 20, because they're both into one group of men with high cholesterol. And the last one is nearly normal. And in order to do that, we have to enter the data into your calculator. And then we're going to look at a normal probability plot. Remember that when we do stat plot, that's the last one on the stat plot. And I need to look at both sets of data individually. So I need to draw a sketch of both of the graphs. Zoom 9. And my first group A kind of looks like straight enough. This is group A. Make sure you label the graphs when you draw them. And let's turn on the other one. Look at list 2. This is B, and it kind of looks like that, straight enough. So we say the normal probability plot is straight enough. So we're going to probably have to go back and forth between some slides here. So then we can say, since conditions are met, a T model is appropriate. I'll move this up just a little bit for now. So since conditions are met, and how did I know I was using a T model? Well, because I'm looking at means, and they're independent groups. It's not the same person. Like they're comparing the placebo group to a different group. So now we're looking at a 2-sample t-test. A T model is appropriate. I will use a two-sample t-test. And this is a t-test for a difference of means. And we have our means already and our standard deviations. We also have the data. So we've put the data into the calculator, so we don't really need to do this by hand. But that being said, I'm going to do it by hand, just to remind you guys of the formulas. So my t-score is going to be my 10.20. That's the mean up here. Okay, let me clear up some of this space. I apologize for... Okay. Our t here, 10.02 minus the 16.4, because that's how we subtracted in, or 0.4, in our hypotheses, and then divided by our standard error, which is going to be 7.66 squared over 10 plus 9.40 squared over 10. And that's going to give us our z-score. All right, so I did that in the calculator. I got negative 1.617. And then I'm going to do TCDF, negative 99, because it was less than, so the negative 99 is going to go first. Negative 1.617, comma 18 degrees of freedom. And remember that that's in second vars, down to TCDF, comma 18. All right, so I got 0.0616. Now I did it by hand. It doesn't hurt to go over and just check it real quick with my t-test, my two-sample t-test. We have the data in list 1 and list 2. I did a less than test. Calculate, and I got the same exact numbers, so that makes me happy. So that means our p-value is 0.0616, which is greater than our alpha. So I'm going to write our conclusion on the next slide, and maybe I'll even type it for you. My handwriting gets really bad on this thing. Since my p-value of 0.0616, it's really important you actually put that number in there. Is it less? Nope, it's not less. It's greater. My alpha of 0.01, much greater than that now. I fail to reject the null hypothesis. Okay, so there is not enough evidence to convince me the mean reduction in cholesterol is not the same for the placebo and treatment groups. That's going to be my conclusion. On the AP exam, you don't have to create a confidence interval even if you do reject, but we failed to reject, so I definitely wouldn't need one in this case. So that was a two-sample t-test for a difference of means. And here is an example of a z-test. Some boxes of cereal include a voucher for a free video rental inside the box. The company that makes the cereal claims the voucher can be found 20% of the time. That's info about our null hypothesis. However, based on their experiences eating the cereal at home, a group of students believes that the proportion of boxes with the voucher is less than, so that's our info on our alternative hypothesis. The group of students purchased 65 boxes of cereal to investigate the company's claim. Students found a total of 11 vouchers out of 65, so p hat is 11 out of 65. That's our sample proportion. Suppose it's reasonable to assume that the 65 boxes purchased by the students are a random sample of all boxes of the cereal. Based on this sample, is there support for the student's belief that the proportion of boxes with vouchers is less than 0.2 provides statistical evidence? So we're going to do a hypothesis test. H naught is P equals 0.2, and HA is P is less than 0.2. And notice that my hypothesis is not P hat, it's P, because I'm trying to make an assumption. I'm trying to test a hypothesis about all of the boxes, the population, not just my sample. My sample was 11 out of 65. We know what that is. It doesn't give us an alpha level, so let's set one of 0.05. We're going to check conditions. Don't forget your conditions. So random is stated, or it's stated that it's assumed that we can assume random. 65 is less than 10% of all boxes of cereal. And you need to write out the whole sentence. You just can't say 65 is less than 10%. You need to say what it's less than 65% of. And then our last condition is NP and NQ. So we have 65 times 0.2, which is greater than 10. That is 13 greater than 10. And 65 times 0.8 is greater than 10. That is 52 greater than 10. So since conditions are met, a normal model, we don't say Z model, we say normal model, okay, I'm running out of space, appropriate, I will use a one proportion z-test. And my formula for my z-score is my sample. Let's find out what that is. 11 out of 65.169. So 0.169, my sample, minus my hypothesis, 0.20, divided by, now when I do my hypothesis test, this standard error, I use my hypothesized value because I don't believe that it's not the proportion at this point. So 0.2 times 0.8 divided by the sample size of 65. And when I do that, I get negative 0.624. And then I do normal CDF. It was a less than again, so negative 99 comma negative 0.624, and that's in second vars. Negative 99 comma, I like using my second answer. So our p-value is 0.266. So once again, my p-value is greater than my alpha, so I fail to reject my null hypothesis. There is not enough evidence to convince me that the vouchers are not in 20% of the boxes of cereal. So once again, since my p-value of 0.266 is greater than my alpha of 0.05, I don't know why it's putting that point somewhere else, I fail to reject the null hypothesis. There is not enough evidence to convince me the proportion of boxes with a voucher is not 0.2. All right, there you have it, a summary of hypothesis tests. Hopefully this helps us out.